This lecture is going to be on vibration and waves. We're going to be looking at pendulums and doing a pendulum lab. We're going to determine that these are oscillators that vibrate. So what is a pendulum? Well, let's look at the anatomy of a pendulum. We're going to make sure we recognize we have a pivot point. This is where the pendulum is attached to a fixed point as it moves around. So it's going to be here. Here we'll call this frictionless. Equilibrium position. Equilibrium position is where the pendulum, or the plumb bob, which we'll learn about here in a moment, is completely vertical. So the pendulum that is hanging vertically, when the pendulum is at equilibrium, it does not mean that it has to be at rest. It can be moving instantaneously at equilibrium as it oscillates back and forth. The plumb bob, that's the object that's doing the moving. That's at the end of the string of the rope. That's the object on here. Amplitude, that's the angle at which the plumb bob is moving from. It's noted as this, right? So we can change the amplitude as well. And damping. Damping is how friction decreases the amplitude over time due to friction. And this can be both air resistance and friction at the pivot point. More often than not, it's friction at the pivot point. Often, many pendulums are explained using the language of assume friction is negligible. So we would say that that would be frictionless. So, vibrations. A vibration is a repeating back and forth motion about an equilibrium position. A vibration cannot exist in an instant. It requires time to move back and forth. So, an oscillator. So we're looking at these highlighted words. These are terminology. So an oscillator is a system that exhibits harmonic motion, whereas a pendulum swings through the equilibrium position, swings through it, and reverses its position and swings back. So, a wave. A wave is a disturbance that is transmitted from one place to another with no actual transport of matter. Instead, it's energy moving through matter. So if we look at the pendulum in the picture, analyzing the picture, the pendulum swings back and forth through one cycle. The pendulum transforms energy from gravitational potential energy to kinetic energy as it oscillates back and forth. We're going to be using terms such as phases of an oscillator. To be in phase means that oscillators are found at the same location as they move. So these two in this picture would be considered in phase. But to say they're out of phase, to be out of phase means that oscillators are not at the same location as they move. And the picture above shows two pendulums that are 180 degrees out of phase. So this video here that I'll load that you'll make sure you'll need to check out is going to talk you through in phase and out of phase. So we've graphed motion throughout the year. Typical linear motion graphs. So here we've said that this object here, the slope is increasing, so is its speed. Here we would say that there are three segments, each traveling at constant velocities. Steeper would be faster, slightly slower, and this one here would be stopped. Whereas a harmonic motion graph would be these patterns that are oscillating about an equilibrium position. That this would have some irregular pattern to it, and this would be more of a constant pattern. It simply would be an oscillation. When graphing harmonic motion, there is some form of repetitive motion, which is why it's termed harmonic motion. It is important to understand the labeling system of a graph to comprehend what is taking place with the oscillator motions. Generally, your y-axis here is going to be the amplitude. So, some examples of harmonic motion in our day-to-day life. The Earth-Sun motions provide examples of harmonic or repetitive motions. We can say day and night, day from the Earth's axis rotating around an internal axis, and night as we orbit the Sun. Right, which leads to a year. Years are repeating. And we can talk about lunar cycles as well. Sound waves disturb air molecules as they travel through them. Your world is based on harmonic motions that you will become familiar with in this unit. So here we see a sound wave traveling through air as the medium. So as we go back to pendulums, why does a pendulum oscillate back and forth? Well, if you notice this plumb bob, if it's pulled back here, its weight is always downward, and there's a net force from tension in the string inward. The restoring force keeps the pendulum swinging. Restoring force is related to the weight and the lift force, or the tension in the string. So you've got forces acting of tension and weight. You should notice that the tension force is slightly larger than the component of gravity. The fact that the tension force is greater than the perpendicular component of gravity means that there will be a net force which is perpendicular to the arc of the plumb bob's motion. This must be the case since we expect that objects that are moving along circular paths, right, this is moving along a circular path as it oscillates, will experience an inward or centripetal force. So back to why does a pendulum oscillate back and forth? Well, notice that tension, F of t, is greater than the F of g in the pictures below. You'll see that this force, this one, the tension, is going to be greater than the downward force of gravity, the weight. If you were to draw the path of the oscillating pendulum, you would see that it is moving in a circular path. And since all circular motion is driven by a net inward force, this should make sense as to why. So if I read below here, the force of gravity is always directed downward. Its magnitude never changes. The tension force is always directed toward the pivot. Its magnitude varies over the course of the vibrational cycle. Here we're going to view two pendulums swinging, and you're going to see that they swing at different rates and they're swinging at different amplitudes. So my y-axis here is going to be amplitude. Notice this pendulum here is going to have a much larger amplitude. Notice this one here completed 4 cycles, or in this case 4 periods, much quicker than the graph at the bottom. So we're looking at the different frequencies and we're looking at the different amplitudes, and these will be covered on the next lecture.